but I did the preliminary work towards that, which is what I'll quickly present. Will not go through all the details of taking the exercise of taking inputs from you, etc. So the whole idea is, as I said, you've gone through a whole lot of physics and math courses in your high school and then in Georgia Tech as well in your first couple of years. And you, especially related to structures, you talked about a few equations, right? And those equations obviously involve certain variables, it involves certain constants. So you're essentially trying to correlate them in order to solve certain problems. So some of those will be known, some of them will be unknown, and you're trying to determine the unknowns in terms of the knowns by manipulating those equations. It could be a single equation for some problems, it could be multiple set of equations which you're trying to solve simultaneously for some other problems. Some of these equations could be algebraic equations, like what we had in this case. We were trying to solve the third, fourth and fifth rows simultaneous linear equations. Some of them could be more complicated algebraic equations involving higher order polynomials or whatever. Some could be differential equations, some could be integro differential equations, whatever, or combinations, algebraic and integro differential also. But whatever they are, essentially we are going from reality to a model, and when doing that we are bringing in a few constants, we are bringing in a few variables, and we are describing a particular state of the structure because it has certain boundary conditions, it has certain loads. Okay, it's made out of a certain material, it is of a certain geometry, right? And then you are essentially trying to find out certain things about it, maybe the stresses, the strains, how long this structure will last, will it get damaged, if so how soon, various kinds of questions, and it depends on how particular problem is framed. You will see that some problems, whatever was known, might become an unknown in a different way of framing the same problem. Okay, so first thing that I would like you to loudly think for yourselves, based on all the courses that you have done, all the readings that you have done, etc. What are the variables which describe any structure which is mechanically loaded? Okay, so in other words, there can be other types of loading, right, like thermal loading, all those things. We'll keep that aside for a while not to overcomplicate the situation, but those can be incorporated in it if and when necessary. But right now it's purely mechanically loaded, which means there are certain forces, there are certain moments. Some of these could be concentrated, some of these could be distributed, some of these could be normal, some of these could be shear, doesn't matter. But there are essentially a whole lot of loads, whole lot of boundary conditions, which could be like clamped or simply supported, or all kinds of combinations. You could have two beams coming together, or a beam joined to a plate, like it is in the case of the wing, let's say, where you have the skin and then you have the stringers or things running around. This is essentially a beam plate kind of a combination, or a beam shell kind of a combination. So the first question is all about variables which describe a state clearly. Okay, so then just list them out. May or may not be comprehensive because you always might leave out something. So that's why it's a teamwork, where you might remember some, he might remember some. So essentially you're putting them all together in order to get as comprehensive as possible, right? Feasible within the short time. So essentially, remember, we talked about modeling in three levels: micro, macro, meso and macro, right? So you've already done micro mechanics, on which you did a homework as well. Then mesomechanics is what we are dealing with all those assumptions and reducing your C matrix to the simplest form that can be. There are a couple of more assumptions which I'll go in briefly in next class, which are again the red zone, which is the danger zone, hazy kind of assumptions. So we will just skip that and gone on to this, because this is important for your take-home final. So the next thing is, now that we have listed all of those in a single list, can we do a bucketing? Okay, so we talk about 4 buckets into which we want to put them, and you will see in the way that I've conducted those exercises by getting inputs from all the students. Without naming those buckets, I've started putting them in 4 different columns and eventually named them, and then essentially people then tend to see, okay, so that comes under that bucket. So even though it has a seemingly different name from the rest of the items on that bucket, it all belongs to a particular category of variables, so which is what we want to get into, categorization or sets. The next thing that we typically do in that exercise is to see what are the 3 sets of equations relating these 4 sets of variables. Now, as I said, we first get the entire list of variables, then we bucket them into 4 columns. Once we do that, obviously these 4 columns that are going to be there are going to have some correlation between them. And how they get correlated in a mathematical model is through equations. So if you have 4 columns, they are connected to each other in a series or a sequence, then obviously the first column is related to the second column through one set of equations. Second is related to the third through another set of equations. Finally, the third column is related to the fourth column through a third set of equations. So now we have 3 sets of equations. Now can we also loudly think about all the kinds of equations that we've been dealing with. For example, we talked about constitutive law, we talked about let's say in some of the things that we have done, compatibility equations we talked about, which are violated when you make the plane stress approximation. So various equations, equilibrium equations, kinematic equations, etc. So we want to see all those equations that we have generally used to solve for the unknowns in terms of the knowns in any kind of problem, be it problems that you have done as part of homeworks, problems that you have done as part of exams, or problems that you have just read through in a book in a self-study, or seen as worked out as examples in a class. So essentially, now that you have 4 buckets of variables, you have 3 buckets of equations that are correlating these, so that then you see the bigger picture of how things are networked amongst themselves, right? So once you have done that, the next thing that you do is so next thing that you do is, now you have those equations, we will see what are those equations dependent upon. Obviously, if they are correlating column A with column B, they of course involve some variables from column A and some variables from column B, but they might also involve certain constants and things like that. For example, the simplest case is one column, let's say, is involving a stress, the other column is involving a strain. They are correlated by a C matrix that we talked about, so it involves a constant, right? So you have those variables, sigmas and epsilons. You have an equation, Hooke's law, sigma equal to C times gamma. Okay, now you have that C is identified as a constant that equation depends upon. So what do these equations depend upon for their form and parameters? And if we look at, for example, the way we have talked about the constitutive law, we said that it's all about the material, nothing to do with the geometry, shape, size, etc. It's purely a material property. So that constant, in that case, the Young's modulus, is a material property, right? So this is what I want to say when I'm talking about dependency. What does it depend upon? Does it depend on the geometry? Does it depend on the material? Does it depend on just the natural laws, for example? So those kinds of things. And finally, so at the so finally what we look at is 4 important quantities, those variables that we talked about, which help to describe the structure, even though they might seem like totally different names, very kind of unrelatable between them. Essentially, they will all fall under these 4 buckets. One is a set of loads, the other is a set of stresses, other is a set of strains, the other is deformations. Okay, deformations. So now you see that there might be a few variables which are kind of hazy because they are not kind of fundamental variables. For example, let's say bending stiffness. Bending stiffness, for example, involves a Young's modulus and a moment of inertia, EI, right? So you talk about a material property and a geometric property, right? But E itself is something that is a fundamental variable, and I itself is dependent on the geometry in terms of the size and the shape of the structure, right? So you can see that there are some which may not fall under these, but they might have be under multiple kind of things as well. That's fine. You put them in both the buckets then, okay? Then you see that we talked about the 3 equations which relate these 4 buckets of variables. Those 3 equations which are first of all, one which relates column A to column B, that is loads to stresses, is your equilibrium equations. Then the one which relates the stress to strain is what we have spent the last few classes on, which is the constitutive law, that C matrix that we talked about. And then finally the strain displacement relationship, which also I wrote out in yesterday's class. We talked about Green-Lagrange strains, so just the linear part, the quadratic part, etc. So that's essentially relating the strain and the deformation, right? Now, in addition to the equations which are governing these within the structure, there are certain things that happen at the periphery. Okay, so those are what we call as boundary conditions, and there are two types of boundary conditions at the two ends. One is the natural boundary conditions, the other is the geometric boundary conditions. This is quite clear to see what it is. It's about the geometry. It means I can say a particular edge or a particular corner or a particular surface is not having any displacement. It is having zero displacement. So that's essentially example of a geometric boundary condition. On the other hand, at a particular location, I might be specifying what is the pressure acting or what is the force acting, which is essentially a natural boundary condition. It's the loading conditions that you're expressing. So in addition to the equilibrium equations, which relate either depending upon the problem, it could be a static equilibrium or a dynamic equilibrium, but essentially relating the loads that are getting applied from the environment to the structure and how the structure is reacting to it, which is what the stress is. So this is Newton's third law parlance. This is your action, this is your reaction. Every action has an equal and opposite reaction, and they are related to each other in some form of an equilibration that takes place between them, static or dynamic. Similarly, here the kinematics, which relates the strain to the deformation, involves those geometric boundary conditions as well, apart from the definitions of the strain itself in terms of the displacement field. Then we next remember in terms of the questions that we asked, what do these equations depend upon? Because we know what these equations correlate. For example, equilibrium correlates loads and stresses, but what does it depend upon? What do the equilibrium equations depend upon? What does the constitutive law depend upon? What do the kinematics depend upon? These depend upon entirely different aspects of the problem, which is what we want to get into this. The first one, the equilibrium equations, natural boundary conditions, are entirely dependent on the conservation laws. They could be the law of conservation of translational momentum or rotational momentum or energy. So essentially there's a conservation laws, which is why you have the law of reciprocity. In other words, what Newton said about action and reaction, right? On the other hand, as we have seen in today's class and yesterday's class also, the constitutive law involves a matrix C, which is all about material properties. Okay, so in other words, the constitutive law is entirely material dependent. Your stress-strain relationship at its pristine level, at its three-dimensional level, doesn't depend on the geometry, it depends only on the material. But then, of course, we talked about in the fiber diameter, how when we keep on reducing the fiber diameter at a particular level, it becomes very, very small, that surface defects per unit area or unit volume become very, very small. Then you saw that there is some geometric implication there. But if you truly look at it, it's actually the surface microstructure, and it's actually a material behavior that we are actually talking about. So in that sense, the constitutive law at its pristine form is material dependent, but over and above that it can become. On the other hand, the strain deformation relationship, where we said that gamma ij is equal to 1/2 of dou ui comma j plus uj comma I plus um comma I times um comma j. Okay, so that's the Green-Lagrange strain or any other strain you define. It's all consisting of derivatives with respect to x1, x2, x3, which is essentially talking about a geometry. So derivatives are nothing but slopes. Okay, so essentially you have a curve and you're looking at the slope of that curve. That's something to do with the geometry of that whole thing. So this displacement relationship with strain, or for that matter deformation in a more enlarged sense for, let's say, an elastic body, can involve rotations as well. So that's why I put it as deformation. It involves both displacements and rotations. Okay, so that will depend upon the geometry, and that's the main takeaway from this. So hence, amongst these three relationship sets that we have, namely equilibrium, constitutive, and kinematics, only one of them depends on the material, and therefore that's the only one which is going to change when you change a material from even the type of the material from an isotropic metal to an anisotropic composite. All that you're going to do is to change that constitutive law. Your kinematics remains the same, your equilibrium equations remain the same, all that you have learned, most of it remains the same. It's only that C matrix that we are talking about that's going to change once you change from a metal to a composite, as long as this is healthy, and that's essentially what I would like you to. I think with this slide I will stop. So there's a reason why the constitutive law is different for a metal and a composite, any material. By MTL here I mean material. So the two main reasons are essentially heterogeneity and also anisotropy. Okay, so in other words, going from point to point, the properties even in the same direction will change, because at one point you might be within a fiber, at another point you might be within a matrix. So there's a heterogeneity, which is why we did the equivalent homogenization in the micromechanics problem. We came up with an imaginary material called the E composite, which is having the same material everywhere, which is somewhere in between the fiber and the matrix, okay, whose properties we could derive using all those laws of isostress and isostrain, right, from Voigt and Roos. Now, on the other hand, that's how that can be taken care of. It's a heterogeneous material or non-homogeneous material. The other is it's not isotropic, and that can also be taken care of by introducing subscripts for your various things that you already knew. You knew the simplest form of constitutive law in a much earlier class as the Hooke's law, where you just said sigma equal to E times gamma, where E is the Young's modulus, the constant of proportionality between sigma and gamma. Now, all that you're doing is, instead of talking about E, when you go to a composite, you're talking of a E subscript L, E subscript T, a G subscript LT, nu subscript LT, etc. Right? So you're just introducing subscripts to show that all these properties are direction dependent. Okay, which is how these what non-homogeneity or heterogeneity means is properties vary even in the same direction. Properties will vary from point to point. On the anisotropic material, if the properties even at the same point will vary from direction to direction. Okay, so how you take care of these is resolved by introducing, in the case of the heterogeneous properties, the equivalent homogeneous material, which is nothing but all that you're doing is an averaging out of things, right? So because you get to a composite property which is somewhere in between these based on the volume fractions. Some might be reciprocal law, some might be direct weightage law. So that's what you end up with. And if you go in a more rigorous way, then what you're actually doing is stresses and strains are, remember, point valued functions. At a given point, at a given instant in time, you have a particular value in the different directions, the stresses. Similarly for the strains. But if you take a small volume around that and you do an averaging out, that volume will include a fiber, will include a matrix, and will have the same proportion as the volume fraction in the entire composite. So therefore, you're averaging it out and getting to a new hypothetical material, which we call as the composite, and its properties were obtained. So that's essentially because we are volume averaging the stress, volume averaging the strain, and therefore we are volume averaging the constitutive law or the stiffness C matrix that you have. How is anisotropy resolved? That because that's the new thing that is coming when you go, second new thing that is coming when you're going from metal to composite. That's by bringing in the direction dependent moduli. So instead of just a single E, you're talking of a EL and ET. Instead of a single G, you're talking of a GLT and a GTT prime. Okay. So instead of a single Poisson's ratio nu, you're now talking of a nu LT and a nu TT prime. So by bringing in those direction dependent moduli, you're taking care of this. So this is all that the overall exercise that you're going to have as a homework is going to be, just to think of all the variables, all the equations, bucket them into these 7 columns that you talked about. So 4 of them are variables, 3 of them are equations, and then you see how they can correlate and explain it in the way much better than the way I have explained it probably in those videos. Okay. And think of this not just as a final for this course, but something that you can carry out of this whole study abroad program or even your undergrad program itself, because it's something that you can really be proud about and something that will become a mnemonic for you, even if you just make it like a poster and put it somewhere. Anytime you get confused about something, you just see where, in which bucket it falls, and then things at a flash make you solve the problem much quicker and much more efficiently. Yeah. Thank you. Any questions, doubts on this, the homework?
You will go into detail like next
Yeah,
class.
sure. Thank you.